All right, this is Mr. McCord's ICP class, Unit 4, Assignment number 5. We're going to start off with a little analogy. So, at some point in your life, you have probably collected something. For instance, I've collected rocks, minerals. I like the little things I can find on the side of the street, off on the highway, parking lots, wherever I can get stuff. So I've got some rock samples here. And in my collection here, I've got 10 spots, and right now I've got 8 of them filled up with samples here. So I'm missing 2 spots. Now, what's exciting is when you can get a full set in a collection. In this case, it would be my 10 rocks here, all right, to fill up these 10 spots. Finding those 2 ones that I'm missing is going to be satisfying. It's going to be exciting. For you, it might be Pokemon cards or baseball cards. It could be figurines. It could be anything, really. But no matter what it is, it's satisfying to be able to finish out a collection, to be able to display it and say, okay, I've got everything I need right here. Now, I'm a huge dork, obviously, so I've got a collection of beakers here also. So I've got a 1,000 milliliter beaker, an 800 milliliter beaker, down to 600, 400, 250, 150, 150 milliliters. And this is my complete set of beakers. I've got them all nicely lined up. And I've got 8 of them total. Now, if I were to miss 2 of these, it wouldn't be quite the same. Having just, this nice kind of descending order and then this really small one. And it'd be even worse if I was missing, like, the 3N ones. It's like, oh, okay, I just got 5 beakers. If it's not the full set, what's the point? Okay? Atoms also collect things, and they love to have full sets of that thing. The thing they collect is valence electrons, and they like to have a full set of valence electrons. For most atoms, a full set is 8 valence electrons. All right? Now, starting a collection is also hard work. When you're at the beginning, you don't have really anywhere to start off of. You've got to kind of build from the ground up. So when you are just kind of getting rolling on it, it's kind of not as satisfying. You're like, okay, well, I've got 2 or 3 of these things now, but there's so much more to go. So atoms also have a tendency to not want to start a collection that they could easily just give up on. So atoms will tend to either gain valence electrons or lose valence electrons, whichever is easiest, to either make a complete set of 8 valence electrons, or will just give up everything and lose their valence electrons to drop back down to 0. Okay, so up to this point, we have assumed that all the atoms that we deal with are neutral. In other words, they have just as much positive charge as negative charge. If an atom like chlorine has 17 protons, it's got to have 17 total electrons to go with that. But when we're looking at atoms collecting electrons, we're specifically looking at valence electrons. So for something like chlorine, to figure out how many valence electrons it has, we have to look at the periodic table. Since chlorine is in column or group 17 of the periodic table, the halogens group, it has 7 valence electrons, just like everything else in that group. Okay? So we're starting with 7 valence electrons kind of collected. So this is where chlorine is starting for now. Now, our atoms are going to want to either gain or lose those valence electrons to either get a complete set of 8 valence electrons or give up what they've got and settle with no valence electrons at all. Well, atoms are not particularly hard workers. They're not going to put in more effort than they need to. They kind of go with the flow of what the laws of physics dictate. So, if chlorine is got to either gain or lose electrons, it's already pretty darn close to 8 valence electrons, it's going to gain a valence electron. if we're going between these two options, it's way easier to gain one valence electron than to try and lose all 7 that it has. Okay? So chlorine is going to gain a valence electron. Now, valence electrons are the same as any other kind of electron. They're no different. So they're negatively charged, which means some things are going to change about the atom. Typically, our atoms have been neutral because all our positive cancel with negatives. But now we have an extra electron on top of that. So they're no longer going to be neutrally charged. They're going to be a little bit positive or negative. There are 3 particles in atoms that we can change the number of to get a different kind of atom. We have protons that change what element we're dealing with. So if you have a different number of protons, you've got a different element. If you have a different number of neutrons, you're dealing with the same element, but it's a different version, a little heavier or a little lighter. We call that an isotope. When we change the number of electrons and we give the atom a charge, either positive or negative, we call that an ion. So chlorine is going to become an ion by gaining 1 valence electron. Okay. Now, we want to know how charged this ion is going to be, since, after all, charge is how things move around at the atomic level. It's how things attract and repel each other. So if this atom of chlorine is suddenly going to be charged, we want to know if it's positive or negative. Okay? So we have to give this a little bit of thought. If we are gaining electrons here, in this case gaining 1 valence electron, we started with a charge of 0. A neutral atom is not positive or negative. Okay? But if our atom is gaining an electron, okay, and an electron is negatively charged, plus a negative is going to be more negative. We're going to get a negative number, a negative charge. This is going to be a negative ion. A little negative sign there. Okay? So we're going to make a negative ion out of this chlorine atom. So to figure out what kind of charge this chlorine atom is going to have, we started with a neutral charge, 0. We are adding just 1 valence electron. And that 1 valence electron has a negative 1 charge. So we are adding a negative. All right? We are gaining something, but that thing is negative. It's kind of like when you get an extra homework assignment you weren't expecting, or you get told to do more chores than you were planning and you want to do something fun. You gain something, but it's negative. So our chlorine is going to be more negative. 0 plus a negative 1 is going to be negative 1. Okay? So this chlorine ion is going to have a negative 1 charge. That's what this means. Now, we say net charge because there's a lot of stuff with charge in the atom, protons and electrons. So it's not like those are really gone. It's just that we are saying positives are canceling with the negatives, and this is what is left over when all of that stuff cancels out. Okay? We had positives and negatives canceling to be 0, and then we threw in 1 more negative thing. So altogether in a net, our net charge is going to be negative 1 for this chlorine ion. Okay? Now, we also have a specific name for a negative ion. We call it an anion. Right? Kind of looks like anion, like someone spelled onion wrong. But we pronounce it anion because we want that ion part to still be an important piece of that word. So chlorine is an anion. It's just a negative ion. All right, next up is lithium. We're going to see how lithium becomes an ion by either gaining or losing valence electrons. If we find lithium on the periodic table, it is in the first column, the first group, called the alkali metals group. So all of those elements in there, including lithium, have one valence electron. So we're sitting about right here. So if lithium is starting with one valence electron, it would be way harder for it to gain 1, 2, 3, 4, 5, 6, 7 valence electrons compared to just losing that one. Okay? So it's going to take the path of least resistance. Lithium is going to lose one valence electron in order to become more stable. Now, it's going to be a little bit different, but since we are changing the number of electrons, our charge is going to be different. So we are going to make an ion here. All right? So our lithium is going to lose its one valence electron. And I can figure out what charge this ion is going to have, kind of like what I would with chlorine. But in this case, since I am losing that one valence electron, instead of adding, I'm going to subtract here. My atom starts neutral. And then I subtract the number of valence electrons that I am getting rid of. Again, the valence electrons are negatively charged. So I am losing one negatively charged electron. So it's going to flip the sign. Minus a negative makes a positive. Okay? So this is going to turn out to be a positive ion. It's kind of like when you de-stress, when you get your homework or your chores done, then you feel kind of a weight off your shoulders. You've gotten rid of something, all the stuff you had to do, but you feel more positive. You feel better about it. So lithium has lost an electron that was negatively charged, so it becomes positively charged in the process. So lithium's net charge overall is going to be its starting neutral charge, where all the positives and negatives canceled, minus the negative one charge of the one electron that it lost. 0 minus negative 1 is going to be positive 1. Okay, so this lithium ion, this charged atom, is going to have a positive 1 charge. Right? Now, just like with our negative ions being called anions, we also have a name for positive ions here. We call them cations. Again, we want to kind of keep this ion word intact. So the way it's spelled, it kind of looks like cation, but we're going with cation. If you are trying to keep straight which one is cation, which one's anion, which one's positive, which one's negative, I'm going to put little cat ears on my cation because cations are positive. You know, like a cat has paws, the ears on the C, so it's like a cat. Anyway, so if that helps, great. If it doesn't, you can figure out your own method. It's kind of dumb, but it's easy to remember. So, okay, let's do 2 more examples. First, we're going to look at sulfur and how it becomes an ion, and then we will look at boron and how it becomes an ion. Okay, same ideas as before. We look at how many valence electrons we're starting with, whether it's easier to gain or lose electrons, and then we figure out whether it becomes a cation or an anion, depending on, whether it's gaining or losing, and we look at what the net charge is going to be based on how many electrons you are gaining or losing. So in sulfur's case, sulfur is in group 16 of the periodic table. It's in the oxygen group. So it starts with 6 valence electrons. So it's a little bit lower than chlorine, but it's still going to be easier to gain 2 valence electrons than it is to lose 6 valence electrons. So that's what sulfur is going to do. It's going to try and gain 2 valence electrons to become more stable. Sulfur gains 2 valence electrons. When it gains those 2 valence electrons, its net charge changes. It becomes charged as an atom, and again, we call that an ion. Since it is gaining negatively charged electrons, it's going to become negative. We call that an anion. And how negative it becomes depends on how many electrons it takes in. So if our sulfur is gaining 2 valence electrons, we start with a charge of 0. I'm adding those 2 electrons, and each of those electrons has a -1 charge. So if I've got 2 electrons being picked up, I'm adding -2. Well, 0 plus -2 is -2. So as an ion, sulfur is going to pick up 2 valence electrons. It's going to gain those valence electrons, right, to become an anion with a -2 charge. Right? Let's look at one more. Let's look at boron. On the periodic table, boron is in the 13th column after the transition metals. Right? It's in the boron group, which is fitting. It's at the top of that column, so we give it that name. Right? So boron in the 13th column starts with 3 valence electrons. Okay, which is quite a bit, but still way easier to lose 3 valence electrons than to gain 5 valence electrons. We always go with whatever is easier. To gain 5 or to lose 3, we're going to lose 3. So boron is going to lose 3 valence electrons. Okay. So its charge is going to change. And this charged atom of boron, this boron ion, okay, as it loses 3 valence electrons, goes from having a neutral charge of 0 to having minus from losing those electrons. Each electron has a negative charge, so 3 of them means they're going to have a -3 charge. And remember, minus and negative flips the sign. So minus -3 is going to become +3. So this boron ion, kind of hard to say, is going to have a +3 charge. And if it's a positive ion, this is also called a cation. So boron becomes a cation with a +3 charge by losing 3 valence electrons. Before I wrap up this video, there are a couple of weird cases I want to talk about just to kind of wrap this up. So we've got elements on the periodic table that start with 1, 2, 3, 4, 5, 6, 7, and 8 valence electrons. So what do we do if we have something that has 8 valence electrons? Well, it's already kind of there. It's already kind of happy with the way it is. It's pretty stable. So if something has already reached 8 valence electrons, like your noble gases in the last column of the periodic table, then they don't usually become ions. That's not to say that they never react or do anything fun for us, but typically we don't look at them becoming ions, positive or negative, by gaining or losing electrons. They're already there. They've already kind of got the complete set. Okay? Helium is included in that, even though it only has 2 valence electrons. Typically, it's pretty good, which is why we put it over in the noble gases column. The noble gases are like the royalty of the periodic table in terms of being very stable. So they don't really associate, they don't bond, they don't do anything with other chemicals. They're just fine being the way they are. They're kind of the cool kids of the periodic table. Okay, so helium and all the other stuff below it with 8 valence electrons pretty much just stays there. It's just not going to become an ion. And I typically won't ask questions about it because they're not really going to do anything. Okay, so that's kind of one reason I avoid the 18th column for this kind of stuff. Something else I avoid is stuff with 4 valence electrons. Something like carbon or silicon can be really tricky to predict because it could gain 4 valence electrons or it could lose 4 valence electrons. So which way is it going to go? It's kind of the same difficulty both directions. Well, that is a question for higher level chemistry classes, and typically we just look at what happens and then figure it out from there. More often than not, carbon, silicon, things like that will become positively charged by losing electrons, but that's also not true all the time. So just know that I will not ask questions about stuff with 4 valence electrons. Okay, focus on 3 and below and 5 and above.